Okay, so let's start by giving you an example in simple regression. So the relationship that we want to study is again the price size relationship. So in the below I will use xi to call sizes and yi to call the prices of house I. Okay, so the data we have is here. These are xi's and these are yi's. Somehow we want to know what's the relationship between them, and if we are given an x, how may we predict y? Okay, so we want to do that in the best way or in the most precise way. I'm going to define what's the best way. Suppose we do an assumption and assume that the relationship between the two variables is somewhat linear. Okay? In that way, we are assuming that we have this equation. What's that? For every xi and yi pair, they are related with this linear equation. Yi is a constant beta 0 plus xi times another constant beta 1. And then there is a random noise epsilon I. Okay, this is simply saying that given x, plug in that into a linear function, okay, to somewhat estimate and predict y. And of course, in reality, it's impossible for xi and yi to really lie on a straight line. So for many observations, there are some deviations. Then that deviation will be captured by epsilon. So if we are talking about the real facts, then we can say epsilon I is a random noise that disturbs the outcome of this linear relationship. Or if we are simply talking about calculations, then after we have this and that, epsilon I is simply the error. So suppose we say, yeah, x and y seems to have a linear relationship. How about this? Let's say beta 0 is 100 and the beta 1 is 2. If that's the case, for every xi, okay, here I sort xi from small to large. Then for every xi, I can calculate 100 plus 2xi. Okay, 100 plus 2xi, that's exactly this one. Okay, given my choice of beta 0 and beta 1, I can calculate 100 plus 2xi. Then, for each observation, for each house, I have that particular epsilon I as the difference between yi and 100 plus 2xi. Okay, I can calculate epsilon I for all those values. If we try to visualize that selection, then the line here, okay, y equals 100 plus 2x is here. Okay, it somewhat passed through this set of points. Okay, somewhat passing through the set of points. And for example, for the first point, 46, the deviation is here. Okay, this particular difference is 24. Okay, this line underestimate the first price. For the second price, it's also an underestimation, but for the third price, it's an overestimation. Okay, this number here is negative 23. That means our estimated value, 218, is greater than the true value by 23. We can expect that when we want to simplify or summarize the relationship into one single line, then of course there will be some deviations or errors for all the observations. Okay? Then the question would be very simple. For which line do we have the somewhat overall smallest deviation? Okay, that's our question. So we don't really know whether 102 is a good choice. Okay, But we can see that, for example, here, many points are underestimated, and some points are really largely underestimated. So we probably should shift the curve upwards a little bit. So how about this? We are allowed to choose these estimations as 102.4. Okay, in that case, this curve will shift will shift counterclockwise, and then we get this curve. I mean this line. Now we can try to compare whether this one is more precise than that one. Then we need a way to somehow summarize or aggregate all those deviations or all those epsilon I. Okay? Then very naturally you will think about the following way. Some numbers are too large and some numbers are too small. This is very similar to the case that we want to summarize the variability of a variable. So for all those epsilon I, let's take the square of it and then sum them up. So that means we are trying to calculate the sum of squared errors just here. Okay? For each I have the true value yi and the estimated or assumed value y hat I. Okay, if we define y hat I as the value calculated with xi and the model. And then for the deviation, we square it and then sum them up. Our goal will be to find beta 0 and beta 1 such that this sum of squared errors can be minimized. Okay? Because we are trying to find the least way to sum up those squares. So this particular principle is called the least square approximation. Okay? This is the way we define the best estimation in regression, or at least in linear simple regression. Okay? We try to find beta 0 and beta 1 so that the sum of square error is minimized. This is called the least square approximation. So for 102, we can do the calculation and find that the sum of squared error is 1 at 16,000 and blah blah blah. If we switch to 102.4, the SSE is going to become smaller, right? It's just 15,000 blah blah blah. Okay, if you want, I encourage you to somewhat verify these two numbers. Okay, you may use Excel, you may use R. Very easily you can calculate these two numbers. But then that did not really answer our question. Our question is that what's the best beta 0 and beta 1 so that this number is minimized, right? We certainly cannot try and error. We need a systematic way to solve it. So, fortunately, there are closed-loop formulas for that. Okay, mathematicians, statisticians, they have found a way. They have found a simple formula that can easily allow us to calculate beta 0 and beta 1. If we are using software, then for today, almost all the statistical software has some functionalities for you to do regression. If we are using R, we can simply use the function called LM, stand for linear model. Okay, linear model. It's not very easy to explain to you why we are calling this function linear model, because this is somewhat advanced. But anyway, simply memorize its name, LM, linear model. Or if you are using Excel, we need to open the add-on data analysis and then use that particular function, regression. Okay, we will provide you a document about how to activate your data analysis. So don't worry. So below, let me do some demonstrations. Suppose I want to use R. Then I only need to write down 3 lines of codes. First, store those values into a variable size. Then store those variables into price. Now I have the 2 variables with values. What I should do is to call lm and specify that my formula is to use size as my independent variable to estimate, to explain, to predict price. Okay? The grammar is that you need to use a tilde to separate dependent variables with independent variables. The output of this particular function will be here. Okay? I call lm with this particular formula, and then the outcome, my coefficients, will be this one and that one. And obviously this is our estimated beta 0 and this is our estimated beta 1. Okay? This is close to 102, but with this particular function we can really find the best or the least square estimate. We're going to call it beta hat 0 and beta hat 1 as 102.7 and 2.2. Okay, this is the best estimate. Something to keep in mind is that what we were talking about is that we say y is beta 0 plus beta 1x with some random noise. Okay, when we are saying something like this, beta 0 and beta 1 are something hidden. Okay, if we have all the data, if we have the information for all the houses in this particular region, then we can say we know what's beta 0 and beta 1 because we can do the least square approximation. We can really calculate these two numbers. But here we only have a sample data, a set of sample data. So what we are doing is sample, is through sampling we do an estimation. Okay, these are my estimates of the population data, of the parameters. Okay, so it's somewhat need you to be careful. Add heads to this beta 0 and beta 1 so that we really know. These are from the sample data. These are just estimates. Okay, but anyway, this is the best we can do because we only have those sample data on hand. If we are using Excel, then it's very similar. We first put all those data into a particular place. Okay, here we will only use price and size. We're going to open that regression function and say our y variables are prices, okay, A1 to A3, and our x variables here are B1 to B13, 13. Here, because the first row contains labels, not numbers, so we need to check it so that Excel knows that it should take the first row as the variable name. Okay, as the variable name. Once we click OK, it will show, it will display a particular report to us. There are a lot of information, but two particular numbers are just the coefficients beta 0 hat and beta 1 hat. Okay, we can see in R in Excel they are producing exactly the same outcome. So now we got those two numbers. It's time to do some basic interpretations. First, graphically, we somehow feel that, oh, this is really the best line that passing through all these points. Okay, this minimizes the square root and squared arrow. Okay, so now we have our regression model, blah blah blah, or something like this. We're going to summarize it as y equals 102.7 plus 2.2x. Okay, this is our conclusion about the relationship between x and y. Some observations here. First, when the house size increases by 1 square meters, the price will be expected to increase by around $2,200. Okay, this is what we got from the formula. When the house size increases by 1 unit or by 1 square meters, we now can say for how much we expect the price to go up. Okay, now we really have a quantitative description about how x affects y. We have more than correlation coefficient. We now can say how x affects y. This is something correlation coefficient cannot do. And also now you may need to be careful in interpret all those results. For example, suppose you say, okay, let's plug 0 into this x, then y would be 102.8, right? That means if I have a house whose size is 0, then the price would be expected to be 102,000. That's definitely wrong, right? That's definitely wrong. So this gives us the first example about a bad interpretation of a regression model. One general guideline is if our sample data only lie in this region, okay, for x, it's basically roughly from 14 to let's say 40 to 110. Then whenever someone asks you to predict what's going to happen when x is 20, when x is 10, or when x is 150, it's dangerous. When you want to do prediction outside your domain of x, it's dangerous. Okay, so keep in mind that you may not overinterpret your outcome. But if someone asks you to answer, what if your x is 80? Then you probably can be safe to say, okay, then I can predict the price would be somewhat within blah and blah. Okay, so your lower bound and upper bound of your x variable definitely play a role in using your regression model. Okay, so now we know simple regression is nothing but a least square estimation. Once we have the intercept and the coefficient for x, we can do interpretations like this. We can understand, we can say how x affects y. Okay, in the next video I will talk about what will happen if we have more than 2 variables. Thank you.